Hey folks, welcome back. This is the last bit of the morning session on day 2 of Social Networks and Health, and we're really pleased to have Jeffrey Smith from the University of Nebraska-Lincoln here to help us think through missing data on networks, and in particular how one might impute missing data. As I said on the intro the very first day, the assumption of network analysis is that you have complete data on a full population, and that's never true. So we need some solution to fix that. And Jeff has been working really hard on this problem with a number of colleagues that we've both had. It's great to see Jeff again. It's sort of like old home week. He was an alum of this group way back in the day. So Jeff, welcome and thank you much.
Thank you, Jim, for the introduction. Yeah, I remember when DNAC was like a couple people in a room. It was like you, me, Lynn, and Peter and Miller. Yeah, so it's come a long ways for sure. It's great to see. And yeah, so I'm happy to come and share a little bit of work on missing data and imputation. And basically the plan was I was going to do 5 to 10 minutes kind of summary of the problem and some overview of possible solutions, simple to more complex. I kind of had assumed folks had watched the videos, but that might not be as true as I thought. That's okay. We'll fill in details along the way. But I'm also happy just to stop and open it up for Q&A if folks have kind of particular problems or questions about missing data in their own work. And if there aren't, that's fine. I might just hint at how one would do this in R. So I have some slides that kind of overview of the more detailed R code that I have up on the DNAC website. All right, so I'm gonna, with that said, I'm gonna go ahead and share. Ooh, can I not share my screen, Jim? Is that not possible? I was assuming I could.
I'll fix that, sorry.
Nah, that's okay.
My only solution, I think, is to make everyone co-hosts. So I think all of you are probably getting now like recording messages and things that you never wanted, but there you go.
Okay, so hopefully you see slides. Yes, okay, very good. It's only been 3 years of Zoom, and you never know. All right, so let me go ahead. Okay, so excellent. All right, so let me just kind of give you a brief overview of the problem that we're trying to solve. And I will say, yes, this is kind of joint work with Jim as well as John Morgan, as a series of papers on missing data and its effect on network measures, and then the last bit on imputation. All right, so let me start with the problem that we're trying to solve, and it's a common one, and then I'll get into the options. And I'll just sort of hint at where we're going, that simple options can be surprisingly effective. So I'll just lay it out there right at the start. Okay, so what problem are we trying to solve? As Jim hinted at, that network data are often incomplete. So we often assume with our measures and our models that we have the full set of actors and the full set of relations, whatever that is, between them. But this is often, often untrue for super practical reasons. And so in this talk, and in most of the papers, we've really focused on non-respondents. Okay, so this is a case where some subset of the nodes or the actors that you're trying to collect data on, there's really no information on who they would have nominated. So they're outgoing ties. And so the sort of iconic case is you go into a high school or a school and you're collecting friendships or who they like and dislike in the school, and some subset of the actors refuse, I don't know why, but they refuse to do your survey, and there's no information from them on the network portion. Let's say we don't have information on who they would have nominated as friends, or who they like, or who they dislike, or whatever the relation of interest is. Okay, so there's missing data in that sense, and this is very common. You might find a typical study has 15 or 20% or more of incomplete information. Okay, and All right. So it's a common problem. If you ever analyzed, or collected your own data, you probably have dealt with this or at least seen this. All right. So the claim from our own work is that the effect of missing data is maybe not as bad as we, in the past may have thought. It doesn't, just because you have a bit of missing data doesn't mean your study is over and you kind of pack it up. But it does cause problems, and it is something you take seriously. And of course, you want to minimize any bias that might arise from having an incomplete set of edge information. All right, and so I won't sort of belabor the point, but a very quick kind of visual demonstration of what missing data might why it might be a problem. So the left hand side, you see kind of full complete network. That's the ideal case. The right hand side is what it might look like. So I've colored the nodes here red if they're non-respondent, so no information. Imagine you collected data and everybody who's colored red here, we get no information on so their network ties going out, who they would have nominated had they had they done the survey, or what the real tie actually is. We don't have any, assuming we have no information about that. Why might this be problematic if you have some part of the full network missing as an analyst? So the left-hand side, again, is that still the complete network, but I've highlighted the non-respondents. The right-hand side is what that same network looks like if you basically remove those or don't take into account those non-respondents in the constructed network, and you sort of plotted. So why might that be problematic for things like centrality or cohesion or distance or whatever you're trying to measure? Well, just kind of looking at it, the observed network on the right, that's the one that the analyst actually sees, looks less dense. It's the path structure might not be quite right, looks less cohesive, and sort of more obviously there's an isolate, or looks like an isolate who's in fact not an isolate. So if you just took your data, you remove those folks who didn't have any information, didn't fill out the survey portion, it would look like the network on the right. And you might think that there's an isolate who in fact isn't an isolate. This happens to be tied to two folks who were non-respondents. Okay, and so this can create bias in sort of classic summary measures: centrality, centralization, component size, distance, various cohesion measures. If you're trying to identify the most important nodes for an intervention, you might get the wrong, pick the wrong folks because your measures, your input data is off, it's biased in some ways. If you're trying to use the network you collect as an input to a simulation for infection spread or diffusion, if you have incomplete or partially observed network structure, there's biases in the path structure and what distance and cohesion and so on. Then if your input network is wrong, then you run the risk of having inference about infection spread and so on also be off. Okay, so it's potentially a problem. We'll leave it at that. And okay, so what to do about it? So that's the problem side. What are your options? And there's a number of things. I'm not going to show kind of every possible option you might do in terms of imputation, but what kind of possible solutions might you try? And I'm going to kind of go through this just at a high level sort of quickly, and then see if there's questions, and then if not, I'll look into how do you do this in R. But what might this look like? What might this look like in terms of you're an analyst, you have the incomplete data, you have missing information, you want to impute in order to minimize bias. What kind of options are there? And I'm just going to run through this visually because I think that's easier. And the assumption is that we're dealing with non-respondents in the data. I am assuming that while there are non-respondents in the sense that there's no information about who they would have nominated as friends or who they like or whatever, I am assuming that there's information going the other way, that respondents, people who did fill out the survey, they often are able to nominate or say that they are friends with and so on, the non-respondents. So basically they're assuming these folks who are non-respondents are still on the roster, we still know about them. So there's some information but there's no information about outgoing ties, but there is information about sort of ingoing ties. That's the assumption that we're working with. Okay, so what to do with it? Let me just go here and kind of walk through what I see as sort of plausible options. Really, I think most of these are fairly simple to implement, which is good. And I'll walk through how to do it and then some sense of the returns to them as well. Okay, so on the left-hand side, what you're seeing is basically the full network. All right, so that's the true network. In this little toy example, we have nodes A through F, and I've colored it just for the demonstration here on non-respondents for E and F, they're red, and all the red edges are edges we don't know about. So they're true, they exist, but we don't know about them because we're assuming they're missing because they're going out from a non-respondent who gave us no information. Okay, so what can you do about it? The very simplest thing, how would you treat this kind of network? You're trying to analyze it, where you basically have information on nodes A through D and some information of edges going from those respondents to the non-respondents. Okay, so the simplest option is what we'll call listwise deletion. That's very easy. You basically just analyze the network by removing anyone you don't have complete information about. So in this case, our non-respondents are E and F. You just kind of remove them from the network. Any edge going to them is not taken into account in the analysis and kind of done. And that's sort of easy to implement. So that's an advantage. The disadvantage is that it distorts the network. Clearly, you're analyzing a subgraph of the network, and path structure and distance and everything is off. And as it turns out, this is a really, really poor option. And it's almost always not the thing to do. And it's always better to at least do some type of imputation beyond listwise deletion. So it's easy, but a really poor option. Okay, so what's better? And I'll give you kind of 3 different versions of what might be better. So we call this simple imputation because it's, well, pretty simple to implement. What this is, the logic here is to really push hard on the observed data. And you assume here that you have edges from, let's say, A and D to E. So E is this non-respondent. We don't have any information about who they nominated, but we're going to put back into or utilize that information that we do have about ties going to the non-respondent. So that's sort of the first big step, is to take that information, utilize it beyond what listwise deletion offers. And then the next little bit, once you've done that, is to do a very, very light imputation on kind of the return ties. So for those folks, those non-respondents who got nominated, we don't know if they would have nominated those people back. So we don't know if a tie exists between E and D, for example. And so we have to choose what to do, how to treat that. And so 3 different options. 1, you assume there's no tie going back. All right, so no tie between E and D or E and A. 2, you assume there's always a tie. So we just basically put those ties back and say, look, there's really likely there's a tie there. That's a symmetric option. And finally, it's probably the best option is probabilistic, where you say, look, we don't know for sure if those folks who were nominated so D to E, for example, if we would have seen a tie going back, but we can do pretty good by basically saying, well, how likely are they to reciprocate that tie? And the very simplest option here is just to kind of flip a coin based on the observed rate reciprocity and probabilistically say if you were likely to see a return tie from those non-respondents to the respondents who nominated them. And that's a mouthful, but hopefully that was clear. I don't know. Okay, so these are very simple options, very strongly based on the observed data, and then very light imputation on kind of filling in those edges just based on those cases where non-respondents are nominated by respondents and saying, would they have given the tie back? So just a very light imputation. All right, the last option, and then I'll stop talking and see if there's, so if folks want to chat or have Q&A, otherwise I'll keep going. But okay, so the last option is a model-based approach, and this is the bottom bit, and I think it's easier just to kind of talk through. So this is a much more holistic approach. So the simple option, as you can see, it really focuses on those edges between respondents and non-respondents that we sort of know about, and then kind of imputing the type back. And that's sort of it. A model-based approach, much more holistic. It sort of attempts to fill in a much wider part of the network. Not only ties between, those kind of return ties between non-respondents and respondents who nominated them, but also between non-respondents, in this case, potentially ties between E and F, and also potentially asymmetric ties from non-respondents to respondents. So in this case, we might impute a tie between E and C, for example. Okay, so how does this work? Basically, the idea is you take the observed network, so the nodes and edges that you know about, observed, you estimate an exponential random graph model, basically predicting, as you can see, the presence or absence of a tie based on tendencies for tie formation, and kind of give you examples. So what kind of terms might you include, or what kind of features might be of use? Certainly baseline rate of forming ties, but also if ties tend to be reciprocated, so a mutual term, things like homophily, so no match, and abs diff. So what types of things predict ties based on the observed network? Take that model and you use that to basically fill in all the NAs, all the cases you don't know about in terms of the ties, and use that to probabilistically predict where a tie is likely to exist only in those cases where there's missing data. So you basically hold the observed network fixed when you're doing imputing or simulating the network, and you just say, okay, given those missing data, where am I likely to have a tie? And so, for example, if there's strong homophily in the network, let's say on gender or race, and E and D are the same gender race, then we might think though that edge is likely to exist, or more likely to exist between two nodes of really different race and really different gender. Okay, and so this allows you to kind of fill in much wider part of the network. So much likely to be higher returns if interested in sort of larger distance and path structures and these types of, the returns are very higher in those types of measures. It also, the downside here is that it does really require having a good model. So the returns are potentially higher because you're getting be able to fill out a wider part of the network rather than just the little bit that's sort of observed, as in simple imputation. But it does mean you kind of need to know what those tendencies are to have the right terms in that initial ergon, because the simulation is only as good as, or the predictions are only as good, or the imputation is only as good as the model is. So that's sort of the, I don't know if it's a downside, but it's just sort of the realities of going down a model-based approach. Okay, so I'll stop there because I've been talking a while. So let me stop, and yeah, let me see if there's Q&A, or if folks want to hit on anything in particular, and if not, yeah, I'm always happy to talk about doing stuff in R, but I don't know if that's what other folks want to chat about.
So if I might just jump in just real quick, Jeff, thank you very much. You set us up with your summary perfectly. What's the conclusion? Which one should we use?
Okay, good. Excellent. So here's the R kind of bits on how to do this. Very good. So okay, so which one to do? Okay, the short answer is almost everything is better than list-wise deletion. So this, what you're looking at here, is just for centrality measures. A summary of, so on the y-axis we have bias, the measure of interest on the columns, and then percent missing is on the x-axis of each little graph. So as missing data goes up, bias goes up. That's not too surprising. And then each line, hopefully that's clear. Jimmy, do you have a question? Yeah.
Finish what you're saying and I'll jump in after.
Okay. Yeah. So I was just trying to get a sense, like hopefully hopefully the figure is clear. Yeah. And each line basically is the bias under different imputation strategies for that measure under different types of missing data. So the first row is when less central nodes are missing, the middle row is sort of random missing data, and the last row is when more central nodes are missing. Okay, and so the short story here with centrality measures is that list price deletion in almost every case is the worst option, and that's true in kind of most measures. In this case, the complex model-based, this is just basically including a clustering term GWESP, does very well across the board, as does probabilistic. Mostly, it does a probabilistic simple imputation, and so I can kind of give you a summary here. But let me see, Jimmy, your question, and then I'll get a little more details on kind of what scenarios the best options are, because it's not always the unfortunate answer is it's not always like one particular solution is always better across the board. It does kind of depend on the type of network you have and what types of nodes are missing. Having said that, any imputation is better than doing nothing, and some options are more robust, so are always a good option, if not necessarily always the best one. And I would say, yeah, a well-specified model-based approach is pretty robust, as is a probabilistic option for simple imputation. So almost always better than doing nothing, and usually a very good option across the board. But okay, Jimmy, yeah, what's the question?
Yeah,
Sorry.
I mean, it kind of builds on what you're saying there, and I just and kind of the pattern of results you can see there for the centrality, and that is that I assume I'm asking kind of if you could talk a little bit more about the difference in kind of the utility of these for kind of local measures, so clustering, homophily, those sorts of types of predictors, as compared to kind of more global measures, the network like reach and those sorts of things. I'm assuming that different imputation strategies are going to be more successful for different kind of network properties, I guess, and you can, like I said, you can kind of see that on the differences in the centrality measures is part of what led me there.
Yeah, I think that's exactly, that's a really good intuition, that as the measure is more global, so closeness and betweenness, distance, and these types of things, more the model-based approach, the returns to the model-based approach increase. So the more it's local, the more I think you can get away with sort of simple imputation. But even then, like simple imputation using probabilistic options, it's not horrific. I think it's surprisingly robust. But I do think the returns to when would you bother doing a model-based approach? And I do think it's when you're particularly interested in features that range farther out into the network. So, and that is also worth knowing that some measures are just harder to get, even with imputation. So between the centrality, just sort of tougher to, the baseline bias is just higher there. And so, so both the bias is higher there, doing any imputation has a huge return, and particularly good doing model-based. And so all of those things are worth considering in terms of what are the returns to doing imputation and trying to pick one. Not easy, but I think the answer is always do something, and don't just do list price deletion. I don't know.
Awesome, thank you. A little bit of time for more questions. I'm going to throw you an unfair question because I should know the answer to this, but I'm going to see what your intuition might be. A lot of times we're going to construct these measures, centrality scores or whatever else, and then use them later in like a regression model or some such. Do you have any sense on whether or not it would be better to do this imputation and then get the centrality score and then get the do the regression versus doing a multiple imputation with on the scores at the regression stage? You know what I mean, like a standard off-the-shelf multiple imputation.
Yeah, that is an unfair question.
I don't know the answer to it. I mean, the one thing, of course, is that the part of what we're correcting for is the bias in the measure for the observed node. So it's not just that you're filling in the unobserved cases, you're in some ways correcting things like closeness centrality for the people that were otherwise there. So any standard off-the-shelf multiple imputation won't ever correct for that because they won't have that information in there. So it might be that this is the best way to go, even though that would be simpler if you were just trying to fill in.
Yeah, my sense is when in doubt, you should impute on the network itself, just because you're going to use methods that are designed to do to impute on the network, as opposed to generalized multiple mutation, which is just going to take the correlations between the variables and sort of hope for the best. So I would, I don't have a empirical answer, but my intuition says, pick the imputation method designed to impute that type of data the best you can, take those measures, and then put that into the regression. So for example, if you did the probabilistic option or model-based, you'd have, it's stochastic. So you'd have like 100 versions of it or something, or 1,000 versions. And you could just take the centrality scores under each version of the network and use that in multiple versions of the analysis and just summarize over. I think that would be a robust way of thinking about how to do this.
Yeah, it'd be nice to know if we need 1,000 versus 5. just because if what we're doing is, say a community detection on top of it, it could be a real pain in the ass, right? So.
Yes, I think you could. I don't think you need 1,000. Yeah, but yeah, that's a good question in terms of how many. You can get away with, probably much less, depending on how much you're actually imputing and how much variation there's across especially with the model-based stuff.
And one of the nice things, and now I'm going to take off my pedagogical hat and just like my self-wondering hat, and say one of the things that when John and Jeff and I sort of started this work, I think the thing that surprised me the most was how robust a lot of the measures are to some really heavy data. I mean, if you look at you probably didn't notice it, but if you look at the x-axis of that plot, it was going out to 70% missing data. So it's like, you can a little bit of missing data, is not as good as having no missing data, but a lot of these measures are remarkably robust. And so that was a nice thing to discover.
Yes, I completely agree that sometimes, doing imputation is almost always going to be better than doing nothing. But I do think it's surprising how robust some of these measures are to, pretty heavy missing data, which is good, I think. Or a relief. But I still think, when in doubt, you should do a proper imputation before doing analyses.
Maggie has a question there saying, is there a threshold of business when you think imputation or different kinds of models would be a best choice? Jeff, idea on a threshold?
So I don't, I think it's hard to have a specific answer just because, so let me very quickly, so I'll show you some results from forget imputation, just looking at the effect of missing data on bias, and it's tricky. So this is from a paper a few years ago. And so what you're seeing again is that x-axis is percent missing, y-axis is bias, and it's kind of divvied up by the kind of the measure and the type of network and the type of missing data. And so what's hard to say is like, do you need to impute or which imputation? And the hard part is, if you're in this first cluster, you have a large network, you're missing nodes or you have non-respondents or on the fringe of the network, and you're doing, total degree, you don't really need to impute because the bias is so low. Even at high levels of missing data, you can, but it's not going to, the returns or the impetus to do it is lower. On the other hand, if you're in some of these other clusters, then you can kind of see where, at what point would you really need to start thinking very heavily or strongly about imputing. So this is just for centrality measures, but you get similar plots in some of the other measures. You can see, depends on how much bias you think is acceptable, but around 20% for some of these measures, especially these it kind of gets worse in terms of the bias as we go down the rows. And so what my suggestion would be is to first just figure out as a first step, if you did no imputation, likely how much bias is there in the types of network you have and the kind of measures you're interested in. And we do have, so based on this paper, we do have like a little calculator, which makes that hopefully that process easier to gauge how much bias you have. And then if you're above, so given your amount of missing data, who's missing, who's likely to be missing, the measure of interest and the type of network, you can gauge how much bias there is. And if the bias is, above, I'd say 15%, I don't know, that's sort of arbitrary, but if it's above, 15% or something, you might want to think strongly about doing some imputation. So that would be the suggestion, would be to first gauge the bias and then say, well, how much of a problem do I have? And then figure out, okay, what is the sort of simplest, most effective strategy that you can do. Hopefully that answers the question. It's not a number, I guess.
Yeah, that was really great. I asked because I have some data where the amount of missingness ranges from like 0.1% to maybe 2%, which I'd considered quite low and maybe negligible, but I want to be really ensure that I'm being diligent in my approach to how I deal with even small amounts of missing data.
Yeah, so experience says that's a pretty small amount of missing data. I mean, we were considering things like 10%, 20%, even 50% of the non-respondents, like
That's
really heavy
crazy.
missing. Yeah. So I think if you're missing 1 or 2%, unless you're doing something strange or it's a really small network, then it's unlikely to be a problem. That's how
I had been approaching it. I just wanted to, since you're here, I wanted to ask.
No, I think that's right.
Okay, thank you.
Since Jeff mentioned that, I put the link to the calculator that we took essentially all the combinations of factors from that paper and allow you to say, well, my network looks kind of like X. What would we expect the missing data pattern bias to be? So that's what that calculator works. The sad part is the damn thing works on Java. And so depending on what your IT people did, it's probably unlikely that your machine will let you run Java natively. So one of the tasks that will get folded into IdeaNet eventually, probably sooner rather than later, is to reconvert that over to a Shiny app because it's not working as well.
Yeah, I don't think it'd be that difficult, and I think it would be super practically useful. So that's a task that we should do.
Yeah, exactly. All right, great. Thank you very much, Jeff. Really appreciate that. If folks have other questions, or we have thoughts of doing a version 4, 5, and 6 on this series eventually. So if you have like the key missing data questions that you're interested in answering, let us know and we'll fold it into the queue. So.